Good morning and welcome to our webinar. This event is devoted to applications of the finite element simulation system QuickField. My name is Vladimir Podnos and I am Director of Marketing and Support here at Analysis. Together with our support engineer Alex, we will show you how to perform the electric circuit analysis with QuickField. Let me briefly overview the QuickField analysis capabilities. As shown on this slide, QuickField is truly multi-physical package which includes static DC, direct harmonic, AC and transient magnetic analysis, electrostatics, AC and DC conduction and transient nonlinear electric analysis, and also steady state and transient heat transfer and stress, mechanical stress. Many of these types of analysis may be coupled, and you may first calculate the electromagnetic fields and then transfer the geo heat sources for further thermal analysis, or use magnetic forces as loads in the stress analysis. And two of these formulations, AC and transient magnetics, support combination of the field problem with connected electric circuit. This field circuit link is organized by using the field block names in the circuit diagrams. Let me explain it in a little bit more detail. QuickField field simulation problem definition includes three types of geometrical objects: nodes, edges, and blocks. Nodes may be considered as corners of the geometrical shapes. Edges are straight lines or arcs which divide the homogeneous components of the field model, blocks. So blocks are usually associated with the model parts. Conductive blocks in AC and transient magnetic problems are model elements which may carry electric currents. In many practical cases, these currents are affected by not only electromagnetic field distribution, but also by electric circuit outside of the field model. To take into account these effects, these blocks names may be used in the electric connection diagram, and current and voltage on these elements is used in the circuit simulation. Other elements allowed in the QuickField circuit diagram are current and voltage sources, capacitors, resistors, inductors, and connecting wires. As you see on these two slides, now you see the presentation of the circuit connection diagram in QuickField circuit modeler, and here you see the same block, conductor 1, which is part of the field model. So, after you combine QuickField blocks with other circuit elements, QuickField circuit simulator perform traditional circuit analysis, but taking into account the currents and voltages taken from the field distribution. And these parameters are iterated between field and circuit part of the model. My colleague Alex will show this in more detail in his examples after my presentation. QuickField circuit simulator is rather simple, and it doesn't allow nonlinear elements like diodes, transistors, thyristors, and other stuff often used in practical circuitry. And sometimes QuickField circuit simulation is not sufficient, but there is other possibility to perform circuit analysis with QuickField. QuickField features open object interface, which allows external application call functions and operate with objects of the QuickField core. This is implementation of the COM technology, and they call this interface ActiveField. External applications which interact with QuickField core may include Microsoft Office documents with macros, MATLAB codes, or custom utilities written in many modern programming systems. And today we will show you how to use the dedicated circuit simulator in Ngspice together with QuickField field model, and this process will be controlled by Excel macros. This may sound complicated, but don't worry. In fact, it's very straightforward and quite easy to perform, because QuickField is an unique tool which does everything fast and easy and require practical training. And you will see it now.
Our practical part today includes 3 simulation cases of AC analysis and 3 cases of transient analysis. AC analysis cases are the first one, the AC analysis of electric circuit with passive elements and linear voltage and current sources. Then we will perform the AC frequency sweep using our parametric tool LabelMover. And the third AC analysis case is the 3-phase transformer simulation, which includes both the field and circuit simulation parts. And the transient circuit analysis cases for today are the transient analysis of series RC electric circuit, the nonlinear circuit elements, the coil with the thermomagnetic coil, and the last example is the combining of QuickField with the external electric circuit simulant. Now let's move to the first case. And this is the AC analysis of the simple electric circuit containing linear elements and voltage and current sources. There are 3 passive elements: inductor, capacitor, and the resistor. And there are 2 sources, the voltage source and the current source. The frequency of these sources is 50 Hz. Our task is to calculate currents and note voltages. And before we begin, I would like to outline some QuickField specifics. In QuickField, in electric circuit, you should specify the peak values. So here you can see the square root of 2. Second, there is no fixed ground connection in the electric circuit. So you can calculate for each element, you can calculate the electric current passing through the element and the voltage drop between element terminals. And the third specific is that you can solve only coupled field and circuit problems. And the field problem should be of AC or transient magnetic type. So we need to create the fictitious AC magnetic problem with one block in geometry model, but we should not connect this block to electric circuit. So let's start QuickField and create this circuit from the beginning. Here is the QuickField. I will create the new problem. I should specify the problem name and the location of the project. Next, I should specify the problem type. We will perform AC analysis, so I choose the AC magnetics. And here I should specify the frequency, the 50 Hz. To connect the electric circuit to the problem, I should type in the circuit name. Now that's all. Here is the geometry model. As I said, we should create some block, build the mesh in this block, assign some properties to the block and to the boundary of the block. The block will be simply the air, and the boundary will have zero magnetic potential. So I have the field simulation part ready, and now I can proceed with the circuit part. Here in the circuit editor window, I should draw my schematics. Now I have the inductor, the resistor, and the capacitor. I add the elements and connect them with the wire. Also, I have the current source and the voltage source. So this is the current source, and this is the voltage source, and I connect sources to the electric circuit. Now I should assign the values for each element. The current source is 4 amperes. This is the RMS value. I should specify the peak value. So I double click the element and type in the value of the current source. And repeat this for all other elements. For resistor, I type 20. For inductor, and for the capacitor, 6.3662. times 10 to the minus 4. And that's all. My electric circuit is ready. Let's check again. And I can run the simulation. Save all problem files. Now what you can see now is the field simulation part. I'm not interested in the field simulation part, so I switch to the circuit simulation result. Here you can get the value of the voltage and the current for each element. And you can copy the picture of the electric circuit you can copy all the calculated values So this is how you should perform the AC circuit analysis. Now let's move to the next example. It is often the case that we need to calculate not only the single frequency but the frequency sweep analysis to calculate the frequency response of the electric circuit. So here is the circuit schematics of band-pass filter. The filter consists of passive elements, the capacitors, inductors and resistors. And our task is to calculate the transfer function versus frequency. So let's start QuickField and solve this problem just for one frequency first. Now this is our QuickField simulation problem. Let's open the problem properties. You can see the problem type is AC magnetics. The frequency is 4 kHz and the electric circuit is attached. Again, the QuickField simulation project should include the geometry model. We will not connect the body of the geometry model to electric circuit. So we have some body with magnetic permeability and boundary condition. And we have the electric circuit. You see the body is not included in the electric circuit, so this is independently analysis of electric circuit. Now to calculate the transfer function, I connect the voltage source at the input terminals and I will measure the voltage drop on the output terminals. Let's simulate this case. This is the field simulation part. I will switch to the circuit simulation result. Now the input signal has the magnitude of voltage of 1 volt and the output signal has the voltage magnitude of 1.6 millivolts. And these results are calculated at the frequency of 40 kHz. Now what should I do next? I should go to the problem properties, change the frequency, run the simulation again, and measure the voltage. It was 1.6, now it's 1.8, no, it's 2.5 millivolts. QuickField features the LabelMover tool for parametric calculations, so we can automate this task. I will start a LabelMover. LabelMover could perform serial analysis, tolerance analysis, and optimization. I choose the serial analysis. I would like to change the frequency automatically in the range from 40 to 60 kHz and measure the output voltage. So first I select the base problem. Then I should specify the values to measure. I will measure the voltage drop on this element R2. Add values. Choose the element. I would like to measure both the absolute value of the voltage and the phase shift of the voltage. Next, I should specify the steps. I will change my base problem . I will change the problem properties. I will increase the frequency by 500 Hz. And I would like to repeat this step on 20 times. So I will cover the range from 40 kHz to 60 kHz. Now everything is ready to run the serial analysis. I have the base problem. I specify the values to measure and I specify the steps to perform. So I press the Get Result button. Initially, QuickField problems are generated. Each problem features its own frequency. Then each problem is simulated and the values of voltage drop on output terminals are calculated. And all these tasks are controlled by the LabelMover parametric tool. Now everything is ready. We can take a look at the results. This is the output voltage. You can see that initially it was very low, but at some frequency the voltage rises, so we can determine here the pass band of the filter. And you can see the voltage phase. And all the results, of course, you can export to the text file, or you can copy them to the Excel, and here perform the following analysis of the result. With LabelMover tool, you can change not only the frequency of the input signal, but you can also change the parameters of the elements. For example, change the inductance value, so you can perform the frequency sweep or the sweep through element parameters. And we move to the next example. This is the three-phase electric circuit with the transformer. Transformer is the electrical device that transfers the energy through electromagnetic induction. So to simulate the transformer, we need to perform the electromagnetic field analysis. The electric circuit you can see here, and it includes not only the circuit elements, but also the QuickField blocks. And through these blocks, the electric circuit and field model are linked together. So I will start QuickField now. Here's the simulation case of the three-phase transformer. Let's open the problem properties. The problem type you can see is the AC magnetics. The frequency is 50 Hz, and the electric circuit is connected to the simulation. Now let's open the geometry model. You can see, unlike the previous cases, the geometry model contains the transformer drawing. There are blocks that represent the air, the insulation, the core, and the windings. The winding blocks are divided in individual winding turns, and the turns are connected in series. The conductivity of the wire is specified. And these circuit blocks are included in the electric circuit. So these blocks are common for both circuit and field simulation. Field part allows to simulate the magnetic link between coils, and the circuit part allows to connect electric circuit to these coils. Now let's take a look at the simulation result. What you can see now is the field simulation result. I will adjust the field picture so you can see the flux density distribution in the transformer core. These are the peak values of the flux density distribution in the core. I can switch to the momentary values, and I will switch on the animation of the field picture. You can see that in some paths the flux simply changed the direction, and in some parts it is circulating. I will switch on the field lines, and here you can see the leakage field of the transformer. Now let's go back to the circuit result. I switch on the circuit result window, and here you can see the voltages and currents in circuit elements, and also voltages and currents in QuickField blocks in the field elements. Now this was the AC simulation, AC analysis cases. We reviewed the simple AC circuit and calculated the currents and voltages in circuit elements. We performed the AC frequency sweep with the LabelMover tool, and this was the AC analysis coupled with the field simulation, the transformer in electric circuit. Now we move to the transient analysis. And the first case is the transient analysis of a simple circuit containing capacitor and the resistor. The capacitor is charged through the current limiting resistor, and our task is to calculate the current. In fact, this case has the analytical solution. So the peak value of the current is determined by the voltage source divided by the resistance value, and the fading time is determined by the time constant. The total time of the time constant is enough for transient process to finish. And for this electric circuit, the time constant equals to the product of the capacitance value and the resistance value. So the time constant for this circuit is resistance multiplied by the capacitance. It is 450 microseconds. For transient analysis, we should specify the integration time step and the final time step. So we will keep in mind this time constant value, 3 time constant values, when we will specify the time integration parameters. Now I will start QuickField and create this simple problem. I create the new problem. I should give it the name and specify the destination folder. Now I should choose the problem type. I will perform the transient analysis. And I should specify the electric circuit name. Next, we should specify the time integration steps. I remember that the time constant is 450 microseconds. I should choose at least 3 times of this value, so it would be about 1.5 milliseconds. Milliseconds. And to be on the safe side, I just use 3 milliseconds. Now I should specify the integration time step. I believe 1 minus 5 will be enough. To get the accurate result. Again, you should draw some geometry model, even if it is not included in electric circuit. I draw some block, give it a label, and assign the label to the boundary of this block. I build the mesh, assign properties, physical properties, zero potential, and now I can proceed with the electric circuit definition. Here I should draw the electric circuit. It's very simple. It contains only resistor, capacitor, and the voltage source. And I connect the elements with the wire. Now the voltage source value is 100 volts. The resistor value is 4.5 ohms, and the capacitance value is 100 microfarads. So volts, 4.5 ohms, 100 microfarads. Now I can run the simulation. This is the field simulation part, and I will switch on the circuit simulation results. Here you can see how the current changes in time. You can see how the capacitor voltage changes in time. The capacitor is charged till it gets the full charge at 100 volts. And our estimation was correct at about 3 times of the time constant at about 1.5 milliseconds. The phasing process is almost finished. And you can copy all the pictures and the simulation results in the Excel and continue the analysis there. Now, what if we need to simulate the discharging of the capacitor? In fact, that's very simple. You should first charge the capacitor and then discharge it. QuickField supports not only constant value for the voltage and current sources, but also the formulas. So instead of fixed value, I will use the pulse function. The pulse will start at 0 time. It will last for enough time for capacitor to be charged, and then the voltage will drop to 0 and the capacitor will be discharging. The pulse should start at 0 time and finish at 5 milliseconds. Run the simulation again. Now it's correct. I have the voltage pulse 100 volts that lasts for 5 milliseconds, then the voltage drops to 0. So the capacitor first is charged by the current, and then the capacitor is discharging through the resistor. This is the voltage of the capacitor. Initially it is charged and then discharging. Again, our task is to calculate the current in time, but now the inductor is not simply the features the inductance, it's the real inductor. It features the resistance and it features the inductance. And moreover, it has the ferromagnetic core, so the inductance value depends on the current. And to simulate the ferromagnetic core, the real inductor, we need to perform the electromagnetic field analysis. Again, for transient problem, we should specify the integration time step and the final simulation time. And in case of linear inductor, we have the analytical solution, and the peak value of the current depends on the ratio of the voltage source to the total resistance in the electric circuit, and the rise time, the speed of our transient process, depends on the time constant. The total time of 3 time constants is enough for transient process to finish. And for this electric circuit, the time constant equals to the ratio of the inductance value to the total resistance in the electric circuit. So if we calculate this, inductance divided by the total resistance it's about 200 microseconds. The time constant is about 200 microseconds, and we'll keep in mind this value when specifying the problem parameters. Now let's switch to QuickField and perform the simulation. This is the problem properties. You can see the problem type is transient magnetics, and we have the electric circuit connected. Now, unlike the previous case, the geometry model contains the drawing of our coil, of our solenoid. And there are blocks that represents the air, the core, and the winding. And you can see that the winding block is divided in the turns in the winding, and each turn is connected in series, and for each turn the electric conductivity of the wire is specified. And now the core is made of a ferromagnetic material, so it has nonlinear magnetic permeability. This is the BH curve. And this is the field simulation part. Now let's open the electric circuit. In the electric circuit you can see the voltage source connected to the resistor in series with the QuickField block. This is not a simple inductor. This is the real inductor simulated with QuickField. Now let's take a look at the simulation result. This is the magnetic field distribution calculated in the inductor and outside. You can switch on the flux density color map and see what is the flux density inside the inductor. And you can switch on the animation. Let's reduce the speed. Initially there were no current, there is no magnetic flux. Then the current began to rise, and with rising current the flux density increases. You can see it on the time plot how the flux density changed in time, and how the current changed in time you can see in the circuit simulation result. So here are the circuit simulation results. And this is how the currents change in time. You may note that this is not exactly the exponential function. Let's again copy the simulation result to Excel. Now this is how the current changes in time. And here let's type the analytical solution. It should be voltage divided by the total resistance multiplied by this. Okay, I have the voltage of 100 volts and divided by total resistance 10 plus 4.2 and multiply it by the 1 minus exponent of minus t divided by the time constant. And the time constant is this value. Now let's compare both. The red line is the theoretical result, and the blue line represents how the current changes in time in a real inductor. And you may note the difference. They started with the same speed and came to the same value of the current. But in between, there is the difference. And the difference is caused by the saturation of the core. Initially at low current value, the core reached constant permeability. But as the current rises, the core saturated and the permeability decreased. And this you can see on the field simulation part. Again, I will adjust the field picture and switch on the magnetic permeability. And as the current value rises, the magnetic permeability decreases and the inductance of the coil changes. So that was the transient analysis with nonlinear element performed by QuickField. And now we move to the last example, the transient analysis of electric circuit containing nonlinear elements performed with cost simulation with external circuit simulator. QuickField circuit editor is limited by passive linear elements. Some of the elements, nonlinear inductor, the transformer, could be added as the field simulation model parts. And another option to extend QuickField capabilities is to perform cost simulation with some other circuit simulator. So here's the simple circuit. The charge capacitor is connected to the inductor. And our task is to calculate the current in time. You know, this is the real inductor, represented here on the right. It features not only the inductance, but also the resistance. So the equation describing the process in this circuit is presented here. And the solution depends on this value. And in case of the complex value, we will have the oscillating process fading in time. Now let's start QuickField. There are two parts in this analysis. There is the QuickField part. And QuickField task is to calculate the inductance. And to solve this task, we need to perform the electromagnetic field analysis. So this is the electromagnetic problem, and these are the blocks representing the air, the inductor, and the core. And the core is made of ferromagnetic material with nonlinear properties. You can see the BH curve. So QuickField will perform only the field simulation part. And the circuit simulation part will be performed by the Ngspice circuit simulator. Here you can see the Ngspice simulator. The interaction between QuickField and the circuit simulator is governed by the Excel. So here is the Excel file. It contains the macros that invokes QuickField to calculate the inductance, which corresponds to the current value in the circuit. Then it invokes external simulator to calculate the current in this circuit. So the analysis performed step by step. Initially we calculate the current, then we calculate the inductance, then we calculate the current for the next step. So we should specify again the integration parameter, the time integration step, and the total number of steps. Now let's take a look inside our program It's not a very large problem. In fact, the QuickField part is as small as this. We invoke QuickField application. We get the QuickField problem, this problem. And for the QuickField block, we assign the current calculated by the Ngspice. We assign the current for the L1 block. Then we solve the problem, open the results, and calculate the flux linkage. Then if we divide the flux by the current and multiply by the square number of turns, we will get the inductance. So this function calculates the flux and then divide the flux by the current and number of turns and get the inductance value. The inductance value is then, once calculated, is submitted to the circuit file that is preceded by the Ngspice simulator. We write the circuit file with the inductance value and then run the Ngspice simulator to calculate the current value. And this is performed with a small time increment step by step. Now let me show you it in action. I will show you both the QuickField and the Excel file so you can see what is happening. Now here I specify the time integration steps, the circuit parameters, and the circuit is automatically created through this circuit Excel sheet. This is the circuit in terms of Ngspice simulator. Now let's run the simulation. QuickField calculates inductance value and the circuit analysis is performed by Ngspice. There is no electric circuit in QuickField. When the results are ready, we can take a look at the current changing in time and the voltage changing in time. This is how the capacitor was discharging. And you may note that this is not the ideal sinusoidal form, as it would be in case of linear inductor. The inductance of a real coil depends on the current, and when the current value is high, the core is saturated and the inductance value decreases. This example is published on our website. So you can download and modify the code for your purposes. And these are all the examples for today. We simulated 3 AC analysis problem, and we simulated 3 transient analysis problem.